Hello and welcome again to my physics online video lecture series. Today's video we're going to be continuing our discussion of the thin lens, this time by discussing the thin lens ray diagrams. Basically, how do you draw ray diagrams for thin lenses, and this may also help clarify a few of the definitions that we've had for the thin lens. So let's get into it. When we're drawing these ray diagrams for the thin lens, basically we need to have available to us ideally a surface like a tablet or whatever that you can write directly on. So I'm doing this in a very non-optimal way because I'm doing it on a screen while writing on a tablet that is not attached to the screen. And there's not much I can do about that with my setup. This stuff works very well if you have a ruler that you can use to draw things to scale. If you use a ruler, then you actually can kind of solve a lot of image formation problems without ever necessarily going to the equations, and your answers can be pretty precise. With my setup, it's going to be largely more approximate. So thin lens diagrams, we'll say here's my lens, and you really pick a sort of axis that you can call the lens axis, for lack of a better term. Essentially, this line that I've drawn and dashed sort of represents where the lens is going to be, given that we're trying to treat it as a infinitesimally thin lens. The other axis that we need to be able to draw is what's called the principal axis, and that principal axis is generally drawn just perpendicular to your call it your lens axis. And the major things that you need to label on that are the focal length, which should be the same on either side. So this distance gives you your focal length, should be the same side distance on either side of this thing that we've labeled as the lens axis. The other maybe points of interest, you can label a point where these two axes meet. That could help guide some rays in other diagrams. What I'm going to do, I'm going to actually go ahead and copy this little diagram that I've made. And the reason for this is that there's two things I want to be able to draw for this. The first is just simply a diagram that shows what this focal length is supposed to represent. So if I have a ray of light that is traveling parallel to the principal axis and it interacts with the lens, then that ray of light should deflect so that it passes through the focal point, going in one direction or another. And this right here, what I've got is a what we'd call a positive focal length lens or a convex lens. And so light basically enters on one side of the lens and then deflects to pass through the focal point on the other side. And I can draw as many rays as I want. By and large, my assumption is that this is a good focal point, means that the rays are all basically just going to pass through that same focal point. And so that defines the focal point. Now you may notice that I've got two of these focal points. That is because I can also send light through from the other direction. So I could have a ray that comes in like this, and that ray is also parallel to the principal axis. That ray will also deflect so that it goes through the focal point more or less. And so if I have several rays incident from this direction parallel to the principal axis, they will also pass through a focal point, albeit, again, the focal point on the opposite side of the lens from the side that they're incident from. So these are basically your two focal points. They're sometimes labeled in these diagrams as capital F prime and capital F. And again, they're both should be the same distance away from the lens. And you can go look at the lens maker's equation and sort of like reverse everything, like turn your lens around and reverse the signs on the two curvature faces, and what you'll find is that, yeah, it's the same focal length. Okay, so that defines focal length for this kind of lens. There's, of course, another option, and I'm going to actually make note again that this is the principal axis for the lens. There is, again, a second type of lens that you could use, which is some sort of a concave lens like this. This lens tends to defocus light. So again, I'm going to draw a principal axis for the lens. Again, I'm going to draw a dashed line like this to represent like where the rays are going to, for the purpose of my diagram, refract. Refraction, of course, actually occurs at both this surface and this surface, but when you're drawing the diagram, it's easier to just have it bend at one surface, and it works. Let's say that I have my focal points once again here and here. We could call this one now F prime, and this one now is F. And again, the distances are lowercase f away. The difference is, you could argue that this should be labeled as negative f. This thing has a negative focal length. If I have light incident parallel to the principal axis like this, and I hit this lens, the light actually bends away from the principal axis like this. And so you may be looking at this saying, okay, if light is acting as you've drawn it, then in what sense do you have a focal point for this lens? And the answer is that the light bends away in such a way that if I look along these rays that I've drawn and sort of continue them, so I'm going to continue them as a dashed line, and this dashed line is just, it's just like if this line just continued on this way, and if I do the same with this one right here, this line just continues on this way, then what I get is that the basically rays continue through our focal point. And so basically, this is the focal point that goes with this side. If I had rays incident from this way, I'd have the same basic thing. They'd bend away, and this would be the focal point. What we would say here is these are like up here, we could say like a positive or real focus. And then down here, what we have is a virtual focus. Okay, so I had to continue the rays with what are called virtual rays. So this and this are virtual rays, and they go through a virtual focus. Okay, so that's like the first set of diagrams. The second set, and again, I said I would copy this thing over. The second set is basically, what about actually using this to find images, because all I've done with these diagrams is just kind of define focal points and define whether I have a real or a virtual focus. So again, I can come over here, and essentially what you do for finding images, you draw for yourself an object. I'm going to draw the object in blue like this. So this is my object. This distance from here to the lens, this would be my DO. Okay. And then the ray diagram that goes with this, I'll draw the rays again in yellow. I need all my rays to basically start or really pass through this point at the tip of the object. And wherever those rays converge, that's where the image is being formed. So the first ray that I'm going to draw is just parallel to the principal axis. Now that's just the same as any one of these rays that I've drawn up here to locate the focal point. So this ray must deflect in such a way that it passes through the focus, like so. The second ray, what I'm going to do is kind of like the reverse of what I've done here. Like, I have this green ray, it goes through the focus, it hits here, and it passes out the other side parallel to the principal axis. Except for originally I drew it as a green ray going into the lens this way and then passing through the focus. It's reversible. And so my second ray I draw from the tip of my object passing through the near focal point, which is about here. And then it interacts with the axis. Don't worry about the fact that the lens isn't physically drawn to be down here. The lens itself is not being drawn to scale, just the distances. So this has to deflect in such a way that it's parallel to the principal axis. And where these two meet, that's where the image is being formed. Now, as a triple check, I can draw another ray from this object through this point that I've labeled here, and that ray should not actually deflect at the point of the lens, and so it just continues on as a straight line. And so all three meet at basically the same point. I think this one's a little low drawn, so they really should be meeting about in here. But in any case, I've formed an image, which I'm going to draw in lighter blue over here. And this image is now located some distance DI away. So this right here would be DI for image distance. And so this is my image. And since all the rays really crossed here, it's actually a real image, and it is inverted relative to the object. So the object arrow points up, the image arrow points down. And then the other piece of information I could get, this right here would be the height of the object. This right here would be the height of the image. And so I can get the magnification if I wanted to by comparing those. The lateral magnification is defined as the height of the image over the height of the object. And then that in turn is negative of the distance to the image over the distance to the object. I'll draw another one that shows a virtual image, but I'm not going to explain it. It's just going to be the same three rays, but it's to show you what a virtual image looks like. I place my object inside the focal point. This ray deflects to pass through the focus on the other side. I also need to have a second ray that goes through this focal point through the tip here, and that one's going to deflect so that it's parallel to the principal axis. These two diverge, so now I have to draw virtual rays. Where they converge will be the location of the image. The result is that because I had to make these virtual rays to find the image, I end up with a virtual upright image.